settle into the sleepy mind channel. Tonight, we're exploring one of the greatest engineering achievements in human history, a remarkable system that quietly carried fresh mountain spring water across an empire without electricity, pumps, engines, or moving machinery. Nearly 2,000 years ago, Roman engineers built enormous networks capable of transporting millions of gallons of clean water every single day, using nothing more than carefully carved stone channels and the steady pull of gravity. Some aqueducts stretched for more than 50 miles while descending only a few feet every mile, supplying thriving cities with fresh water long before the invention of modern plumbing. At its height, the city of Rome received more clean water each day than many major cities would not enjoy again until the 19th century, making the Roman aqueduct one of the greatest public engineering projects ever undertaken, and one of the greatest reasons the Roman Empire was able to grow into one of the largest civilizations the ancient world had ever known. If you enjoy videos like these, feel free to like and subscribe. We post new sleep stories every other day. For all night listening, be sure to check out our playlists covering history, science, engineering, archaeology, nature, and many of the forgotten wonders that quietly shaped our world. Although almost everyone has seen a Roman aqueduct in photographs, movies, or history books, very few people know what they are actually looking at. The enormous rows of graceful stone arches that have become symbols of ancient Rome were only a small fraction of the entire system. In reality, nearly all of an aqueduct traveled quietly beneath the ground through covered stone channels and tunnels that protected the water from dirt, sunlight, evaporation, and contamination. Hidden beneath hillsides, forests, farmland, vineyards, and villages, these underground waterways stretched mile after mile before occasionally emerging onto magnificent stone bridges whenever a deep valley interrupted their path. Together they formed an artificial river built entirely by human hands, allowing fresh mountain spring water to travel extraordinary distances using nothing but gravity. What makes these remarkable systems even more astonishing is what the Romans did not have. They possessed no electric pumps to push water uphill, no steel pipelines stretching across the countryside, no satellites to map the landscape, no lasers to measure elevation, no computers to calculate slopes, and no powered construction equipment to speed the work. Every route was surveyed by hand using simple measuring instruments. Every tunnel was carved through solid rock by workers using picks, hammers, and chisels. Every stone was shaped individually before being lifted into place. Most impressive of all, the water channel had to descend at an almost perfect angle for its entire journey. If the slope became slightly too steep, the water would rush with enough force to damage the channel. If it became only a little too shallow, the current could slow until it stopped altogether. Maintaining that delicate balance across mountains, valleys, rivers, and open countryside remains one of the finest surveying achievements in the history of engineering. Tonight, we'll follow a single drop of crystal clear mountain spring water from the peaceful hillside, where its remarkable journey begins, all the way to the heart of ancient Rome. Along the way, we'll discover how Roman surveyors measured impossible distances with astonishing precision, how thousands of skilled workers carved tunnels beneath the landscape and raised towering bridges across deep valleys, why volcanic ash helped create concrete that still survives after nearly 2,000 years, how gravity quietly powered an empire's water supply every hour of every day, and why modern engineers continue studying these silent waterways as one of the greatest engineering masterpieces ever created. By the end of our journey, you'll understand not only how Roman aqueducts worked, but why they became one of the greatest triumphs of human ingenuity, proving that with patience, precision, and a deep understanding of nature, one of the ancient world's simplest ideas became one of its most extraordinary achievements. For thousands of years before the Roman Empire reached its greatest size, nearly every town and village faced the same challenge. People naturally settled close to rivers, lakes, or dependable springs because fresh water determined whether a community could survive. Families needed it for drinking and cooking. Farmers depended upon it for their crops and livestock. Craftsmen required it for their trades, while growing populations demanded increasing amounts simply to meet the needs of everyday life. As long as settlements remained small, nearby water sources usually provided enough. But as Rome expanded from a modest city into the center of a vast empire, those traditional sources could no longer keep pace with the needs of hundreds of thousands of people living within the city walls. The earliest Romans relied much like everyone else in the ancient world. Wells reached underground water hidden beneath the city. Natural springs provided clean drinking water where they could be found. The nearby Tiber River offered an additional supply, although its water was often muddy and unsuitable for drinking without treatment. During dry seasons, many wells produced less water than expected, while rivers could become polluted by daily activity upstream. Carrying water also required enormous effort. Every bucket had to be lifted by hand and transported through crowded streets, limiting how much water any family could realistically use each day. As Rome's population continued growing, it became increasingly clear that the city needed an entirely different solution. The Romans soon realized that the answer was not to search for larger rivers closer to the city, but to bring distant mountain springs to Rome instead. High in the surrounding hills, rainwater slowly filtered through layers of rock before emerging as cool, remarkably clean springs. Unlike rivers, these natural springs remained relatively constant throughout much of the year because the surrounding ground acted like a giant natural reservoir. Rain and melting snow soaked into the earth during wetter seasons, then slowly seeped back to the surface over many months. Long before anyone understood groundwater or geology, Roman engineers recognized that these mountain springs produced some of the purest and most dependable water available. Choosing the right spring became the first and one of the most important decisions in building an aqueduct. Engineers searched for water that remained cool, clear, and plentiful throughout every season. They carefully observed how strongly each spring flowed during both wet and dry periods, ensuring that it could continue supplying water year after year. The surrounding land also mattered. Springs located high in the mountains provided an important advantage because gravity could carry the water naturally downhill toward the city. The higher the source, the farther the water could travel without requiring any additional energy. Nature itself would provide the power if the engineers could design the correct path. Once a suitable spring had been chosen, the real challenge began. The shortest route between the mountains and the city was almost never the best one. Valleys, hills, cliffs, rivers, and unstable ground all stood in the way. Rather than forcing the water across every obstacle, Roman surveyors studied the landscape with extraordinary patience. They walked the countryside for weeks or even months, measuring elevations and examining the natural contours of the land. Instead of drawing a straight line, they searched for a route that allowed the water to descend gently and continuously. The finished aqueduct might wind around hills, follow the side of a valley, disappear into a tunnel, or cross a bridge before continuing underground once again. These surveyors occupied one of the most respected positions within Roman engineering. Their work determined whether the entire aqueduct would succeed or fail long before construction ever began. A mistake of only a few inches in elevation could eventually stop the flow of water many miles away. Every measurement, therefore, had to be checked repeatedly before workers laid a single stone. The success of thousands of laborers, craftsmen, and builders depended upon the quiet accuracy of a handful of surveyors standing in open fields with remarkably simple instruments, proving that some of history's greatest engineering achievements began not with construction, but with careful observation of the landscape itself. Roman surveyors achieved this remarkable accuracy using instruments that appear surprisingly simple by modern standards. One of their most important tools was called the chorobates, a long wooden beam fitted with carefully carved grooves and suspended plumb lines. When the strings hung perfectly straight and the water resting inside the grooves remained level, the surveyors knew the instrument itself was perfectly horizontal. From that stable reference point, they could begin measuring the gentle slopes required for the aqueduct. Another instrument, known as the groma, helped establish straight lines and precise angles across the landscape. Although these devices lacked moving gears or complicated mechanisms, they allowed experienced surveyors to measure the countryside with astonishing precision through patience, repetition, and careful observation. Every measurement was repeated again and again before construction received approval. The surveyors understood that a small mistake near the beginning of the route would become a much larger problem many miles later. If an error caused the channel to rise even slightly above its intended path, gravity could no longer keep the water moving forward. Entire sections of the aqueduct might need to be rebuilt before a single drop ever reached the city. Because of this, Roman engineers preferred spending additional weeks measuring the land rather than risking years of expensive repairs after construction had already begun. Their philosophy was simple. Careful planning always cost less than correcting mistakes. Once the route had finally been approved, another enormous challenge appeared. The countryside between the spring and the city rarely cooperated with the engineers' planned path. Gentle hills could often be followed around their sides, but steep ridges sometimes blocked the route completely. Deep valleys interrupted the landscape without warning, while rivers carved broad channels that seemed impossible to cross. Rather than forcing every obstacle to fit a single solution, Roman engineers adapted their designs to the landscape itself. Wherever possible, they allowed the aqueduct to remain underground, quietly following the natural contours of the terrain. Only when the land offered no reasonable alternative did they construct the magnificent stone bridges that have become symbols of Roman engineering. This surprises many people today because the towering arches dominate photographs and history books, creating the impression that aqueducts spent most of their journey high above the countryside. In reality, those spectacular bridges represented only a tiny percentage of the overall system. Building above ground required enormous amounts of stone, labor, and time, making it both expensive and difficult. Underground channels proved far more practical. They protected the water from contamination, reduced evaporation beneath the hot Mediterranean sun, sheltered the channel from severe weather, and required far less building material than elevated structures. Whenever engineers could keep the aqueduct beneath the surface, they almost always chose to do so. Digging those underground passages demanded remarkable determination. Workers equipped with little more than iron picks, hammers, chisels, and baskets slowly carved their way through soil, gravel, clay, and solid rock. Progress often measured only a few feet each day, especially when the tunnel encountered particularly hard stone. To speed construction, engineers frequently ordered crews to begin digging from several different locations at the same time. Vertical shafts descended from the surface to the planned tunnel below, allowing workers to excavate multiple sections simultaneously before eventually connecting them beneath the ground. This approach dramatically reduced construction time, but it also required astonishing accuracy. Tunnels begun from opposite directions sometimes had to meet after hundreds or even thousands of feet, leaving almost no room for error. When modern archaeologists examine surviving Roman tunnels, they continue marveling at how precisely those separate excavation teams met beneath the landscape. Without electronic communication, satellite navigation, or laser guidance, the workers often emerged within inches of their intended target. Every successful connection reflected the extraordinary skill of the surveyors who had planned the route months or even years earlier. It serves as another reminder that the visible structures standing above the landscape tell only part of the story. Hidden beneath the earth lies an equally impressive world of careful measurements, patient excavation, and engineering precision that quietly carried fresh mountain water toward the heart of ancient Rome. As the tunnels gradually advanced through the hillsides, another team of workers remained busy at the surface, preparing the materials that would eventually transform rough excavations into permanent waterways. Quarries echoed with the steady rhythm of iron tools striking solid rock as skilled stonecutters carefully removed enormous blocks destined for bridges, retaining walls, inspection shafts, and other visible structures. Nearby, wagons loaded with freshly cut stone creaked slowly across rough roads toward the construction sites, pulled by teams of oxen capable of moving weights that would have challenged even the strongest groups of laborers. Every block represented countless hours of careful work, long before it ever became part of the finished aqueduct. The Romans understood that selecting the right building materials could determine whether an aqueduct lasted for decades or for centuries. Wherever possible, engineers preferred durable local stone that could withstand constant exposure to moisture without cracking or crumbling. Limestone proved especially popular in many regions because it was relatively easy to shape while remaining strong enough to support tremendous weight. In volcanic areas, builders often incorporated harder stones formed by ancient eruptions, taking advantage of materials naturally available within the surrounding landscape. Transporting stone over great distances required enormous effort, so Roman engineers became remarkably skilled at adapting their designs to the geology of each region where an aqueduct was built. Among all the materials used throughout the Roman Empire, however, none became more famous than Roman concrete. Even today, scientists continue studying this remarkable building material, because many ancient structures constructed with it remain standing after nearly 2,000 years. Unlike many modern concretes that slowly weaken over long periods, Roman concrete often became stronger as it aged under the right conditions. This extraordinary durability helped aqueducts survive earthquakes, changing weather, flowing water, and the passing centuries, preserving many sections long after the empire itself had disappeared. The secret behind this remarkable concrete lay in one unusual natural ingredient: volcanic ash. Around the Bay of Naples and several other volcanic regions, fine ash produced by ancient eruptions accumulated in thick deposits across the countryside. Roman builders discovered that when this ash was mixed with lime and water, it created a chemical reaction unlike ordinary mortar. The mixture hardened into an exceptionally durable material capable of resisting moisture while continuing to strengthen over time. Although Roman craftsmen could not explain the chemistry taking place inside the concrete, generations of experience taught them that this special mixture produced structures capable of surviving conditions that destroyed many other building materials. Modern scientists now understand much more about why Roman concrete performed so well. The volcanic ash contains tiny particles rich in silica and aluminum. When combined with lime and water, these minerals react to form new crystals that gradually strengthen the material over many years. Even small cracks that developed inside the concrete could sometimes seal themselves as water triggered additional chemical reactions within the structure. This remarkable ability to continue changing long after construction ended helps explain why many Roman harbors, bridges, and aqueducts remain standing after almost 2 millennia of exposure to rain, flowing water, changing temperatures, and the natural aging process. Of course, concrete alone could not complete an aqueduct. Skilled stonemasons shaped every visible block with extraordinary care, creating smooth surfaces that fit tightly together with precision. The familiar arches supporting elevated sections relied upon this careful craftsmanship more than massive amounts of mortar. Each wedge-shaped stone, known as a voussoir, pressed gently against its neighbors, transferring weight downward through the curve of the arch until the forces reached the supporting columns below. At the very top sat the keystone, the final block placed into position. Once it settled into place, the entire arch locked together, allowing gravity itself to strengthen the structure rather than pull it apart. This elegant understanding of forces became one of Rome's greatest engineering achievements. Instead of resisting gravity, Roman builders learned to guide it. Every stone helped support the next, distributing enormous loads throughout the structure with remarkable efficiency. That same principle continues influencing bridge construction today, reminding modern engineers that some of the most effective designs are also among the simplest. Standing beneath one of these surviving aqueducts, it becomes easy to admire the graceful rows of arches stretching across the landscape. Yet hidden within that beauty lies a deep understanding of geometry, balance, and structural engineering that has inspired builders for nearly 2,000 years. While the great arches captured the admiration of travelers approaching a Roman city, the water itself remained hidden inside a much smaller structure built along the very top of the aqueduct. This narrow channel, known as the specus, served as the true heart of the entire system. Although the bridges beneath it could stand many stories high, the water usually flowed only a few feet deep inside a constructed stone conduit. Every inch of the channel had been designed to encourage a smooth, steady current that would continue day and night without interruption. The Romans were not interested in creating rushing rivers. They wanted calm, predictable movement that carried water efficiently while protecting the structure that surrounded it. To achieve this, the interior walls of the channel were lined with a waterproof mortar called opus signinum. Made by combining lime with finely crushed pottery and brick, this remarkable material formed a dense surface that resisted leaks while creating a relatively smooth path for the flowing water. The smoother the walls became, the less resistance the water encountered as it continued its long journey toward the city. Even small improvements in the channel's surface reduced turbulence, helping maintain a consistent flow across many miles. Although modern engineers describe these ideas using the science of fluid dynamics, Roman builders understood the same principles simply by observing how water behaved under different conditions. The channel itself remained surprisingly narrow compared with the enormous structures supporting it. Most aqueducts carried only the amount of water actually required, avoiding unnecessarily wide conduits that would have demanded far more stone and construction effort. Engineers carefully balanced the size of the channel against the expected flow from the mountain spring. During periods of heavy rainfall, the water level could rise, while drier seasons naturally reduced the volume. The dimensions of the specus allowed these changes to occur without overflowing or leaving the channel nearly empty. Everything reflected careful planning based upon years of experience with the behavior of natural springs. Protecting the water became just as important as transporting it. Because most of the aqueduct remained covered, leaves, dust, animals, and other debris rarely entered the channel. The stone roof also shielded the water from direct sunlight, helping it remain cool even during the hottest months of the Mediterranean summer. This cooler temperature reduced the growth of algae and helped preserve the fresh taste of the mountain spring throughout its long journey. While many ancient civilizations struggled with contaminated surface water, Roman engineers devoted enormous attention to preserving water quality from the very beginning of the system until the moment it reached the city. Of course, even the cleanest mountain water carried tiny particles of sand, silt, and dissolved minerals, collected during its passage through the surrounding landscape. As the water traveled mile after mile, some of these materials gradually settled along the bottom of the channel, while dissolved minerals slowly formed thin layers upon the stone walls. Left unattended, these deposits would eventually reduce the amount of water the aqueduct could carry. The Romans understood that even the finest engineering required regular care if it was to continue performing reliably for generations. To make that maintenance possible, engineers constructed vertical access shafts at regular intervals along underground sections of the aqueduct. From the surface, these shafts appeared as little more than narrow openings protected by stone covers. Beneath them, however, ladders or carved footholds allowed maintenance crews to climb down into the channel below. Workers entered these passages carrying simple hand tools to remove accumulated sediment, scrape away mineral deposits, inspect damaged masonry, and repair any sections showing signs of wear. These routine inspections helped ensure that small problems never developed into major failures, capable of interrupting the city's precious water supply. The maintenance crews became the quiet guardians of the aqueduct. Unlike the engineers who designed the system or the builders who constructed its towering bridges, these workers rarely received recognition for their efforts. Yet their work proved essential to the aqueduct's long life. Day after day, year after year, they walked through cool stone tunnels, illuminated only by small oil lamps, carefully removing obstructions and checking every section of the channel. Their dedication allowed many Roman aqueducts to remain in continuous operation for centuries, quietly delivering fresh mountain water through changing seasons, political upheaval, and the rise and fall of emperors, all because generations of skilled workers understood that even the greatest engineering achievements depend upon careful maintenance as much as brilliant design. As the aqueduct approached the outskirts of a Roman city, the character of the journey began to change. For many miles, the water had traveled quietly through mountains, forests, farmland, and open countryside, encountering little more than the occasional inspection shaft or bridge. Now the surrounding landscape became increasingly busy. Roads filled with merchants and travelers converged toward the city gates. Farms gave way to workshops, homes, and growing neighborhoods. Yet even as the population around it increased dramatically, the water continued flowing at the same calm, steady pace it had maintained since leaving the mountain spring many hours, or even days, earlier. Before entering the city's distribution system, the water usually passed into large settling tanks, known as piscinae limariae. These chambers performed one final cleaning before the water reached the people who depended upon it every day. As the flowing water entered the wider basin, its speed slowed naturally. Sand, small stones, and other heavier particles gradually settled to the bottom under their own weight, while the cleaner water continued toward the exit near the top of the chamber. The process required no filters, chemicals, or moving parts. Workers inspected these settling tanks regularly because they understood that even a well-maintained aqueduct collected small amounts of sediment during its long journey. The accumulated material at the bottom of the basin could be removed without interrupting the flow of cleaner water above. By cleaning the settling tanks at regular intervals, maintenance crews prevented unnecessary debris from entering the city's fountains, bathhouses, and homes. It was another example of Roman engineers solving complex problems with surprisingly simple solutions based upon careful observation of nature. From the settling tanks, the water entered one of the most important structures in the entire system, the distribution tank, or castellum divisorium. If the aqueduct itself functioned as the highway carrying water toward the city, the castellum served as the central interchange directing that water wherever it was needed most. Built at one of the highest practical points within the city, the tank allowed gravity to continue doing all the work. From this single location, carefully designed outlets divided the flow into separate channels that supplied different parts of the city without the need for pumps or mechanical valves. Roman engineers planned these distribution systems with remarkable care. Public fountains usually received the highest priority because they supplied drinking water to the greatest number of people. Even during periods of lower water flow, officials wanted these fountains to continue operating reliably. Bathhouses, although enormously popular, could tolerate small reductions if necessary, while decorative fountains, gardens, and certain private connections often occupied lower positions in the system. By carefully controlling the height and size of each outlet, engineers could influence how much water reached different destinations throughout the city. For the ordinary citizen, the public fountain became the most visible part of the entire aqueduct. Scattered throughout neighborhoods large and small, these stone fountains provided a dependable source of cool, fresh water every day of the year. Families filled clay jars for cooking and drinking. Travelers stopped to refresh themselves before continuing their journey. Children gathered nearby while merchants conducted business in the surrounding streets. Because the water flowed continuously rather than remaining stagnant, it stayed fresher and cleaner than water stored for long periods inside containers. These fountains quietly became gathering places woven into the rhythm of everyday Roman life. The steady flow also carried another important advantage that is easy to overlook today. Since the water never stopped moving, older water was constantly replaced by fresh supplies arriving directly from the mountains. There was little opportunity for it to remain standing long enough to develop unpleasant tastes or odors. Excess water simply overflowed from the fountains and continued through planned drainage channels before eventually leaving the city. What might seem wasteful by modern standards actually helped maintain cleanliness throughout the system, while ensuring that fresh water remained continuously available to anyone who needed it. Standing beside one of these fountains, a Roman citizen would have seen only the final moments of an extraordinary journey. The water pouring quietly into the stone basin had already traveled across mountains, through tunnels, beneath fields, over graceful bridges, and along measured channels extending for dozens of miles. Every sip represented the successful work of surveyors, engineers, quarry workers, stonemasons, tunnel builders, maintenance crews, and countless others whose efforts remained almost entirely invisible. Like the hidden channels beneath the countryside, the greatest achievements of the aqueduct often went unnoticed precisely because they worked so reliably every single day. While public fountains served everyone, one of the greatest beneficiaries of the aqueduct system was the Roman bathhouse. Today, it is easy to imagine these buildings simply as places where people wash themselves, but they were far more than that. Public baths functioned as the social centers of Roman life, where friends gathered, business was discussed, news spread through the community, and people from many different walks of life shared the same spaces. A single large bath complex could require hundreds of thousands of gallons of water, an amount impossible to provide by buckets or wells alone. As the water entered the bathhouse, it was carefully directed through an intricate network of channels, reservoirs, and pools. Visitors often moved gradually through rooms of different temperatures, beginning in warm chambers before entering hot bathing rooms and eventually cooling down again in refreshing pools filled with cold spring water. The Romans became masters at combining their aqueducts with another remarkable technology known as the hypocaust, an underfloor heating system that circulated hot air beneath stone floors and inside hollow walls. Together, flowing water and controlled heat created bathing complexes unlike anything the ancient world had seen before. Keeping those baths supplied required constant planning. Fresh water continually entered the pools, while older water overflowed into drainage channels, preventing it from becoming stagnant. Unlike many modern swimming pools that filter and reuse the same water, Roman baths depended upon a steady supply of new water arriving from the aqueduct. The constant movement helped maintain cleaner conditions while allowing thousands of visitors to enjoy the facilities every day. Gravity quietly performed nearly all of the work. Water entered from higher elevations, flowed naturally through the baths, and eventually continued onward toward the city's drainage system. The aqueducts also transformed another essential part of daily life that many people rarely consider when imagining the ancient world: sanitation. Before reliable running water became available, keeping crowded cities clean presented an enormous challenge. Waste could accumulate quickly in narrow streets, especially as populations grew larger. The Romans recognized that fresh flowing water could help solve many of these problems. Public toilets, known as latrines, often received a continuous supply of water that carried waste away from the seating area and into the city's sewer system. Although these facilities differed greatly from modern plumbing, They represented an important step toward improving sanitation within densely populated urban centers. Beneath many Roman cities lay another remarkable engineering achievement, an extensive network of underground sewers. The most famous was the Cloaca Maxima in Rome, originally constructed to drain marshland before gradually expanding into one of the largest sewer systems of the ancient world. Overflow from fountains, bathhouses, and public buildings entered these underground passages, where gravity carried the water away from the city. The aqueduct and the sewer formed two halves of the same system. One delivered clean water into the city, while the other carried used water safely away, allowing fresh supplies to arrive continuously. The availability of dependable water also encouraged countless smaller improvements throughout everyday Roman life. Stone basins allowed horses and other animals to drink after long journeys. Gardens surrounding temples, villas, and public spaces remained green throughout much of the year. Certain workshops depended upon flowing water for washing raw materials, cleaning finished products, or supporting specialized manufacturing processes. Even decorative fountains served practical purposes by keeping water moving while providing convenient places where citizens could fill their containers. The aqueduct touched nearly every corner of urban life, often in quiet ways that people gradually came to take for granted. The greatest measure of the aqueduct's success was that most Romans rarely thought about it at all. Fresh water simply appeared at the fountains each morning. Bathhouses remained full. Public spaces stayed cleaner than many cities elsewhere in the ancient world. The engineering hidden beyond the city walls quietly performed its work without demanding attention. Like many of the world's finest inventions, the aqueduct succeeded because it became almost invisible to the people who depended upon it. The success of the aqueducts allowed Roman cities to grow to sizes that would have been almost impossible only a few generations earlier. Before dependable water supplies reached the expanding urban centers, populations were naturally limited by whatever rivers, wells, and local springs could provide. There was only so much clean water available for drinking, cooking, washing, and sanitation. Once the aqueducts began delivering fresh mountain water every hour of every day, those natural limits changed dramatically. Entire neighborhoods expanded beyond the original city walls, public buildings multiplied, and the population of Rome eventually climbed into the hundreds of thousands, making it one of the largest cities anywhere in the world during the ancient era. This steady supply of water also changed the way Roman citizens thought about public spaces. Fountains became gathering places where neighbors met throughout the day, merchants paused during their travels, and children played within sight of the constantly flowing water. Many squares echoed with the gentle sound of streams spilling into stone basins before continuing through carefully designed drainage channels beneath the streets. These fountains were not reserved only for the wealthy or powerful. They served the entire community, providing fresh drinking water free of charge to anyone who approached with a clay jug or bucket. They represented one of the earliest examples of large-scale public infrastructure benefiting every level of society. The presence of reliable water encouraged architects to think differently as well. Buildings no longer needed to stand directly beside rivers or natural springs. Instead, engineers could extend water wherever the aqueduct reached, giving city planners far greater freedom when designing neighborhoods, marketplaces, temples, bathhouses, and public gardens. Hills that once seemed impractical suddenly became attractive locations because water could now be delivered almost anywhere, provided the elevation remained below the source. The aqueduct quietly reshaped the geography of Roman cities, influencing where people lived, worked, gathered, and built for centuries. Agriculture also benefited in regions served by dependable water supplies. Although the primary purpose of most aqueducts was supplying cities rather than irrigating vast fields, nearby farms and gardens often gained access to fresh water that would otherwise have been unavailable. Fruit orchards, vegetable gardens, and vineyards flourished in areas where careful management allowed portions of the water supply to support cultivation. During dry Mediterranean summers, this dependable access helped maintain productive landscapes close to growing urban populations, strengthening the relationship between the countryside and the cities it supplied. Industry quietly expanded alongside these improvements. Roman craftsmen required water for countless everyday tasks, from washing wool before weaving it into cloth to processing leather, dyeing fabrics, preparing food products, and cleaning workshops. While rivers still powered certain mills and larger operations, the dependable flow supplied by aqueducts supported many smaller industries scattered throughout the city. Reliable water reduced interruptions, improved cleanliness, and allowed skilled workers to focus more of their effort on their craft, rather than constantly searching for additional supplies. Like so many other benefits of the aqueduct, these improvements often became part of daily life without attracting much attention. Of course, constructing systems of this size required an enormous workforce organized with remarkable efficiency. Long before the first stones were laid, officials assembled teams of surveyors, engineers, quarry workers, stonemasons, carpenters, blacksmiths, laborers, and transport crews. Each group possessed specialized skills essential to the success of the project. Quarry workers extracted thousands of tons of stone. Blacksmiths forged tools that needed constant sharpening and repair. Carpenters built scaffolding strong enough to support heavy construction high above the ground. Teamsters guided wagons loaded with building materials across rough roads, while engineers coordinated every stage so that each crew completed its work at precisely the right time. Large aqueduct projects often stretched across many years, and in some cases, several decades. One generation might begin surveying the route, another oversee the most demanding construction, and a later generation witness the first water finally entering the city. Few of the workers who began these immense projects expected immediate rewards. That long-term way of thinking became one of the defining characteristics of Roman engineering. Rather than constructing only for the present, they built with the expectation that their work should remain useful for centuries, a goal many of their surviving aqueducts continue fulfilling nearly 2,000 years later. When the first waters finally reached a Roman city, after years of planning and construction, the moment was often celebrated as one of the greatest achievements of the community. Imagine the anticipation as officials, engineers, laborers, and ordinary citizens gathered near the distribution basin, waiting for the first clear stream of mountain water to appear. After traveling dozens of miles through tunnels, channels, bridges, and measured slopes, the water quietly entered the city exactly as its designers had intended. There were no roaring engines or dramatic machines announcing its arrival. Instead, a gentle current flowed steadily into the waiting channels, beginning a journey that, if properly maintained, might continue uninterrupted for centuries. The completion of an aqueduct also became a powerful statement about the strength and stability of the Roman Empire. Emperors and local officials understood that providing clean water improved daily life more effectively than many other public projects. New aqueducts demonstrated that Rome possessed the knowledge, organization, resources, and skilled workforce necessary to reshape entire landscapes for the benefit of its citizens. Inscriptions carved into stone often recorded the names of the rulers who financed these enormous undertakings, ensuring that future generations would remember who had brought fresh water to their communities. Some of these inscriptions remain visible today, allowing historians to trace when particular aqueducts were constructed, repaired, or expanded. As decades passed, the aqueducts became so dependable that many Romans simply assumed the water would always be there. Children grew up drinking from the same fountains their parents had used before them. Merchants opened their shops each morning knowing nearby fountains would already be flowing. Bathhouses welcomed visitors from sunrise until evening, without concern that the supply would suddenly disappear. Ironically, this quiet success was the greatest compliment the engineers could have received. Of course, the Roman Empire itself would not last forever. Political instability, economic difficulties, invasions, and changing priorities gradually affected many regions that had once been connected by Roman administration. As central authority weakened, some aqueducts no longer received the regular maintenance that had kept them functioning for centuries. Channels slowly filled with sediment, vegetation took root in neglected structures, and occasional sections collapsed after earthquakes or severe storms. In certain places, invading armies deliberately damaged aqueducts during sieges, recognizing that interrupting a city's water supply could prove as effective as attacking its walls. Yet even under these difficult circumstances, many aqueducts continued operating far longer than anyone might have expected. Some systems remained in use throughout the Middle Ages, supplying growing towns long after the Western Roman Empire had disappeared from history. Local communities repaired damaged sections whenever possible, recognizing the tremendous value of a dependable source of fresh water. In several parts of Europe, ancient Roman channels continued serving later civilizations that often had little knowledge of the original engineers who designed them. The structures themselves became part of the landscape, quietly performing the same task century after century while kingdoms rose and fell around them. Modern archaeologists frequently describe Roman aqueducts as some of the best preserved engineering projects from the ancient world. Their survival owes much to the quality of their construction. The careful stonework, durable concrete, and thoughtful design allowed many sections to withstand earthquakes, floods, changing climates, and nearly 2,000 years of natural weathering. Even where parts of an aqueduct have disappeared, the remaining foundations often reveal the precision with which Roman surveyors first laid out the route. Every surviving fragment provides another opportunity to understand how one of history's greatest civilizations approached the challenges of large-scale engineering. Walking beneath one of these ancient aqueducts today, it is difficult not to admire both its beauty and its practicality. The graceful arches seem almost effortless as they stride across broad valleys, yet every stone reflects careful calculations made centuries before. Above them, the narrow channel that once carried fresh mountain water appears surprisingly modest compared with the immense structures supporting it. That contrast perfectly captures the genius of Roman engineering. The greatest effort was often devoted to quietly supporting something simple. In the end, the aqueduct was never really about building monumental bridges. It was about delivering clean water reliably, day after day, year after year, with such consistency that generations of people could build their lives around its silent and dependable flow. Although the Roman Empire eventually faded into history, the ideas behind its aqueducts never truly disappeared. Engineers throughout later centuries continued studying the surviving structures, often marveling that they had been built without modern machinery. Medieval builders repaired sections whenever possible, while Renaissance architects measured the ancient bridges and tunnels, eager to understand how Roman surveyors had achieved such precision. Even when portions of the original systems could no longer carry water, the engineering principles they demonstrated continued influencing generations of builders who recognized that some of history's greatest lessons had already been written in stone. During the 18th and 19th centuries, as modern cities began expanding rapidly during the Industrial Revolution, engineers faced many of the same challenges that confronted ancient Rome. Growing populations demanded larger supplies of clean drinking water, better sanitation, and dependable infrastructure capable of serving hundreds of thousands of people. Although modern technology introduced steam engines, iron pipes, and eventually electric pumps, many designers still relied upon the same basic principles that had guided Roman engineers nearly 2,000 years earlier. Whenever possible, gravity remained the simplest, most reliable, and most economical way to move water across long distances. Even today, gravity-fed water systems remain common throughout much of the world. Mountain reservoirs often supply cities located many miles away, allowing water to flow naturally downhill through carefully designed pipelines without requiring constant pumping. Engineers still devote enormous attention to maintaining the correct slope, controlling water pressure, protecting water quality, and ensuring that every section of the system functions efficiently. The materials have changed dramatically. Concrete has become stronger, steel pipes have replaced stone channels, and electronic monitoring now assists with maintenance. Yet the underlying concept remains wonderfully familiar. The quiet force of gravity continues performing the same work it accomplished for Roman engineers centuries ago. One area of Roman engineering receiving particular attention from modern scientists is their concrete. Researchers have spent decades studying samples collected from surviving aqueducts, bridges, harbors, and public buildings, hoping to understand why many Roman structures have endured for nearly 2,000 years, while some modern concrete requires significant repairs after only a few decades. Advanced laboratories have revealed that the volcanic ash used by Roman builders created complex mineral structures capable of strengthening over time, particularly when exposed to water. These discoveries have encouraged scientists to explore new concrete mixtures that may one day improve the durability and environmental sustainability of modern construction. Roman surveying techniques continue earning admiration as well. Yet when they compare those sophisticated measurements with the routes selected by Roman surveyors nearly 2,000 years ago, they often discover that the ancient engineers chose remarkably efficient paths across the landscape. Their careful understanding of terrain, combined with endless patience and repeated measurements, produced results that remain impressive even by today's standards. The greatest compliment modern engineers can offer the Romans is that many of their fundamental ideas remain unchanged. Successful water systems still begin by protecting clean water sources. Surveyors still study the landscape before construction begins. Designers still calculate slopes with extraordinary care. Builders still select durable materials capable of lasting for generations. Maintenance crews still inspect systems regularly because preventing small problems remains far easier than repairing major failures. Technology has transformed the tools available to engineers, but the underlying philosophy has remained remarkably constant. Careful planning, thoughtful design, and respect for the natural behavior of water continue forming the foundation of successful engineering projects throughout the modern world. Looking across nearly 2,000 years of history, the Roman aqueduct achieved something far greater than simply transporting water from one place to another. By understanding gravity instead of attempting to overcome it, Roman engineers created systems so reliable that many continued serving communities for centuries beyond the lifetime of the empire itself. Every surviving aqueduct stands as quiet proof that some of humanity's greatest inventions succeed not because they are complicated, but because they work in harmony with the natural laws that have shaped our world since long before the first stone was ever laid. The influence of Roman aqueducts extended far beyond the cities that first received their flowing water. As the Roman Empire expanded across Europe, North Africa, and parts of the Middle East, engineers carried their knowledge with them, adapting the same principles to different climates, landscapes, and geological conditions. Some regions required aqueducts to cross broad river valleys, while others demanded long tunnels through rugged mountains or carefully supported channels winding around steep hillsides. No two aqueducts were exactly alike, because each landscape presented its own unique challenges. Rather than forcing the land to conform to a standard design, Roman engineers carefully studied each region and allowed the terrain itself to guide the final route. This flexibility became one of the greatest strengths of Roman engineering. An aqueduct built in the dry countryside of southern Spain faced different conditions than one supplying a city in the hills of modern France or the valleys of present-day Turkey. Local stone varied in hardness and durability. Weather patterns changed from one province to another. Earthquakes threatened certain regions, while seasonal flooding challenged others. Instead of relying upon a single solution, Roman builders adjusted their construction methods to suit the environment while preserving the same underlying principles of careful surveying, gentle gradients, durable materials, and constant maintenance. Many of the empire's most famous aqueducts still stand today. The Pont de Gard in southern France rises nearly 160 feet above the Gardon River, carrying water across the valley on 3 graceful tiers of arches that have survived for almost 2,000 years. In Spain, the Aqueduct of Segovia stretches proudly through the center of the city, its precisely fitted granite blocks standing without mortar, while continuing to inspire visitors from around the world. Near Rome itself, long lines of ancient arches still march across the countryside, silently marking the routes where fresh mountain water once flowed toward the imperial capital. For every famous bridge standing proudly above the landscape, there were miles of hidden channels quietly following the contours of hillsides or disappearing beneath open fields. In many places, those underground sections remain buried today, preserved beneath layers of soil, where archaeologists continue uncovering them piece by piece. Excavations frequently reveal beautifully constructed stone conduits that appear almost untouched, despite spending centuries beneath the earth. Their remarkable condition provides valuable insight into how carefully the Romans protected the water throughout its long journey. Modern archaeology has transformed our understanding of these hidden waterways. Ground-penetrating radar allows researchers to detect buried channels without disturbing the surrounding landscape, while aerial photography sometimes reveals faint lines in crops or soil that trace the route of forgotten aqueducts beneath the surface. Three-dimensional laser scanning creates incredibly detailed digital models of surviving bridges and tunnels, allowing engineers to study their construction in ways that would have been impossible only a few decades ago. The aqueducts have also become valuable classrooms for engineers studying the relationship between infrastructure and longevity. Many modern projects are designed with expected lifespans measured in decades before major repairs become necessary. Roman aqueducts challenge those expectations. Built using simple tools, local materials, and careful planning, many sections have survived earthquakes, floods, wars, changing climates, and nearly 2,000 years of natural weathering. Their endurance reminds us that thoughtful design and patient construction can often prove just as important as advanced technology. The Romans built slowly, but they built with the expectation that their work should continue serving people long after the original builders themselves had disappeared. That is one of the quietest lessons carried by every surviving aqueduct. Its true success is revealed over time, through decades and centuries of dependable service. Every stone laid by Roman builders supported not only the channel above it, but also the lives of countless people who depended upon the steady arrival of fresh water each day. In that sense, the aqueduct became far more than a structure of stone and mortar. The Roman aqueduct also changed the way future civilizations thought about public investment. Constructing one required an enormous commitment of time, money, materials, and skilled labor, often lasting many years before the first drop of water ever reached its destination. Yet Roman leaders understood that the rewards would continue long after the construction crews had departed. Every new fountain, bathhouse, workshop, and neighborhood, supported by the aqueduct, strengthened the city's economy and improved daily life for generations. Rather than viewing these projects as temporary accomplishments, the Romans treated them as permanent investments in the future of their communities. This long-term thinking influenced nearly every decision made during construction. Builders rarely searched for the fastest solution if it meant sacrificing durability. Instead, they selected stronger stone even when it required additional effort to quarry and transport. Surveyors spent months refining their measurements because they understood that correcting mistakes after construction would require far more time and expense. Throughout the project, patience consistently proved more valuable than speed, a philosophy that remains familiar to engineers responsible for designing important infrastructure today. The aqueducts also reflected an impressive understanding of maintenance as part of engineering rather than something separate from it. Modern infrastructure sometimes receives attention only when problems become obvious, but Roman engineers planned for inspection and repair from the very beginning. Access shafts, settling tanks, inspection chambers, and removable stone covers were all incorporated into the original design because the builders expected future generations to maintain the system regularly. They understood that even the finest structure could not care for itself forever. By making maintenance easier, they greatly increased the likelihood that the aqueduct would continue operating successfully for centuries. Another fascinating aspect of the aqueducts is how quietly they blended into the natural landscape. Farmers plowed their fields above hidden channels, carrying fresh mountain water toward distant communities. Shepherds guided their flocks across hillsides without realizing that constructed tunnels lay beneath their feet. Forests slowly grew over buried conduits, while streams crossed above them. The water continued its steady journey, regardless of the changing seasons unfolding across the countryside. In many places, the aqueduct became such a natural part of the landscape that people gradually forgot it was there at all. Only when the terrain demanded something extraordinary did the engineering reveal itself dramatically. A broad valley suddenly filled with elegant rows of towering arches. A deep ravine required a graceful bridge stretching from one hillside to another. A mountain blocked the route, prompting engineers to carve a tunnel directly through solid rock rather than forcing the water to climb over the summit. The true genius of the aqueduct lay not in its most spectacular sections, but in the quiet consistency that carried water mile after mile without interruption. Modern visitors often stand beneath surviving aqueducts, looking upward at the massive stone arches, naturally focusing on their impressive height and graceful proportions. There, inside a modest stone channel, no wider than a person could comfortably walk, flowed the water that justified the entire project. Thousands of tons of carefully placed stone existed simply to support a relatively small stream moving quietly toward the city. It is a powerful reminder that truly great engineering often devotes enormous effort to accomplishing something that appears surprisingly simple once it is complete. As archaeologists continue uncovering forgotten sections of Roman aqueducts, they repeatedly discover evidence of the extraordinary care invested in even the smallest details. Mason marks carved into individual stones reveal which craftsman shaped particular blocks. Mineral deposits left behind by flowing water allow researchers to estimate how long certain sections remained in operation. Every new discovery adds another layer to our understanding, revealing that the aqueducts were not static monuments frozen in time, but living systems that evolved, adapted, and continued serving communities across many generations. A remarkable discovery made by modern researchers is just how accurate Roman surveyors truly were. Using satellite measurements, laser scanning, and high-precision mapping equipment, engineers have retraced the routes of many surviving aqueducts to compare modern calculations with those made nearly 2,000 years ago. Again and again, they have found that the ancient builders selected routes requiring astonishingly little correction. The gentle gradients remain remarkably consistent across dozens of miles, proving that Roman engineers achieved a level of precision that still commands enormous respect within the engineering profession. This remarkable accuracy required far more than mathematical ability alone. Surveyors needed a deep understanding of the landscape itself. They learned to recognize stable ground capable of supporting heavy structures for centuries. They observed how seasonal streams changed after heavy rainfall, identified hillsides vulnerable to landslides, and avoided areas where unstable soil might gradually shift beneath the weight of an aqueduct. Every decision balanced engineering with practical experience. The safest route was not always the shortest, and the easiest path was not always the most reliable. Success depended upon choosing a course that would continue supporting flowing water not merely for a few years, but for generations yet to come. The Romans also understood that water itself possessed tremendous power. Although a gently flowing stream appears peaceful, moving water can gradually reshape stone, carve deep valleys, and wear away even the hardest materials when given enough time. Aqueduct designers therefore worked to keep the current calm and predictable throughout its entire journey. Sharp corners were avoided whenever possible, because sudden changes in direction created turbulence. Sudden drops in elevation could increase the water's speed enough to damage the channel, while unnecessary obstacles disrupted the smooth flow the engineers worked so carefully to maintain. Every curve and every change in direction reflected an understanding that controlling water often meant allowing it to move naturally rather than forcing it into abrupt movements. When particularly steep terrain could not be avoided, Roman engineers developed ingenious solutions that went far beyond the famous arches. In other places, they built inverted siphons using sealed pipes that carried water down one side of a valley and back up the opposite slope using water pressure generated by the change in elevation. These systems required careful calculations because the pipes had to withstand tremendous internal pressure without leaking or bursting. Although far less common than traditional gravity channels, inverted siphons demonstrated that Roman engineers possessed a sophisticated understanding of hydraulic principles whenever difficult landscapes demanded more advanced solutions. Another challenge came from nature itself. Throughout the year, changing weather continually altered the amount of water flowing from mountain springs. Heavy winter rains could increase the supply dramatically, while long dry summers naturally reduced it. Engineers designed many aqueducts with these seasonal changes in mind, allowing the channels to carry larger volumes during wetter months without overflowing, while still maintaining sufficient depth during drier periods. The system remained flexible enough to accommodate nature's changing rhythms, rather than expecting the landscape to behave exactly the same every day of the year. This ability to work alongside nature explains why so many Roman aqueducts survived for such extraordinary lengths of time. Instead of attempting to overpower the landscape, the engineers carefully studied it before construction ever began. They followed natural contours whenever possible, selected durable building materials suited to local conditions, protected the water from contamination, and accepted that regular maintenance would always remain essential. Every decision reflected the understanding that successful engineering begins with respecting the environment in which it must operate. Rather than conquering nature, the Romans learned how to cooperate with it, allowing gravity, geology, and the landscape itself to become active partners in one of the greatest engineering achievements the world has ever known. While the Romans perfected the art of carrying water across great distances, they also developed an impressive system for protecting the springs that supplied it. Engineers understood that the quality of the water entering the aqueduct determined the quality of the water arriving in the city many miles later. Whenever possible, they enclosed the source within constructed stone spring houses that shielded it from animals, falling leaves, and other sources of contamination. These structures also reduce the amount of sediment entering the channel at the very beginning of its journey, making maintenance easier farther downstream. Long before scientists understood bacteria or microorganisms, Roman engineers recognized that protecting clean water at its source produced healthier and more reliable supplies. The springs themselves often emerged from limestone hills, where rainwater had spent months or even years slowly filtering through layers of rock beneath the surface. This natural filtration removed much of the dirt and suspended material carried by rainfall, while cooling the water to a remarkably consistent temperature. By the time it reached the spring, the water was often clear, refreshing, and far cleaner than nearby rivers exposed to constant human activity. Modern hydrologists continue studying these same groundwater systems, and many of the springs selected by Roman engineers nearly 2,000 years ago remain dependable sources of drinking water today. Their careful observations proved remarkably accurate, despite the absence of modern scientific instruments. Once the water entered the aqueduct, its journey became surprisingly peaceful. Unlike rivers rushing over waterfalls or streams tumbling through rocky valleys, the current inside the channel moved with quiet consistency. The carefully calculated slope allowed the water to glide steadily forward without creating destructive turbulence. In many sections, the surface would have appeared almost perfectly calm, gently reflecting the stone ceiling above, while continuing its long descent toward the city. A traveler, walking beside certain stretches of the aqueduct, might have heard little more than a soft murmur echoing through the narrow conduit, barely realizing that millions of gallons of water quietly passed by every day. Maintaining this calm flow required constant attention to detail throughout construction. The floor of the channel had to remain smooth enough to prevent unnecessary resistance, while still providing sufficient grip for maintenance workers who occasionally entered to perform repairs. Joints between stone blocks were carefully sealed to prevent leaks that might gradually weaken the surrounding ground. Sharp changes in direction were avoided whenever possible, because every sudden turn disturbed the current and increased wear on the structure. Water pressure presented another challenge requiring thoughtful solutions. Because gravity continuously accelerated flowing water, pressure naturally increased whenever the channel descended to lower elevations. Roman engineers learned to manage these changes by carefully controlling the gradient and, where necessary, constructing pressure relief features that reduced unnecessary strain on the system. In locations using inverted siphons, where water descended into a valley before rising again on the opposite side, the pipes experienced especially high pressures. Construction also demanded remarkable organization beyond the engineering itself. Thousands of workers required food, shelter, tools, replacement materials, and steady coordination over projects that often stretched across many years. Temporary roads connected quarries with construction sites, while workshops repaired worn tools and produced new equipment as older ones gradually wore out. Supervisors coordinated deliveries so that stone, timber, lime, and other materials arrived when needed, rather than sitting unused for months. In many respects, organizing the workforce became almost as complex as designing the aqueduct itself. Success depended not only upon engineering knowledge, but also upon careful planning, communication, and logistics across vast distances. These massive projects brought together people with many different skills who might otherwise never have worked side by side. Surveyors translated mathematical measurements into practical routes across the countryside. Quarry workers transformed solid rock into carefully shaped building blocks. Stonemasons assembled graceful arches whose strength depended upon precision. Tunnel crews slowly advanced through hills from opposite directions, trusting that careful measurements would eventually bring them together beneath the earth. Blacksmiths forged replacement tools, carpenters erected scaffolding, teamsters transported heavy loads, and maintenance crews prepared to care for the finished system long after construction ended. The completed aqueduct reflected the combined knowledge of thousands of individuals, each contributing a small but essential part to one of history's greatest engineering accomplishments. As Roman engineering spread throughout the empire, the knowledge required to build aqueducts spread with it. Young apprentices learned beside experienced surveyors, stonemasons, and engineers, observing every stage of construction before gradually taking on greater responsibility themselves. There were no engineering universities in the modern sense, no printed textbooks explaining hydraulic principles, and no digital drawing showing every measurement. Instead, knowledge passed from one generation to the next through careful demonstration and years of practical experience. An apprentice might spend months simply learning how to recognize quality stone before ever helping construct an arch, while future surveyors practiced measuring short distances repeatedly before being trusted with the route of an entire aqueduct. This tradition of apprenticeship helped maintain remarkably consistent standards across an empire that stretched thousands of miles. Whether an aqueduct was being constructed in present-day Spain, southern France, Italy, North Africa, or the Eastern Mediterranean, visitors would recognize many of the same construction methods and engineering principles. Local materials naturally varied from region to region, yet the philosophy behind every project remained familiar. Build only after careful planning. Allow gravity to perform the work. Protect the water from contamination. Construct with materials intended to last. These principles became the foundation upon which Roman hydraulic engineering was built. One reason these methods proved so successful was that they respected the landscape instead of trying to dominate it. Modern engineering often possesses the machinery to flatten hills, redirect rivers, or reshape entire valleys when necessary. Roman engineers rarely enjoyed that luxury. The aqueduct gently curved around hills, rather than cutting directly through them whenever practical. It followed the natural contours of the land, instead of forcing perfectly straight lines across every obstacle. Only when absolutely necessary did the builders resort to tunnels or elevated bridges. This willingness to cooperate with the terrain reduced construction time, conserved materials, and created systems that blended remarkably well into the surrounding environment. Even after construction finished, the landscape continued influencing the aqueduct throughout its lifetime. Heavy winter rains occasionally increased the flow of mountain springs, while long summer droughts reduced it. Earthquakes shifted the ground beneath certain sections, and tree roots slowly expanded through cracks in nearby stone. Floodwaters sometimes damaged bridges crossing rivers, while mineral-rich water gradually deposited thin layers of limestone inside the channels. Roman maintenance crews expected these natural changes because they understood that an aqueduct was not a structure built once and forgotten. The remarkable longevity of many aqueducts demonstrates how successfully that philosophy worked. Some systems remained in continuous operation for hundreds of years, surviving changes in government, economic hardship, wars, and natural disasters that would have ended the usefulness of less carefully designed infrastructure. The aqueduct quietly adapted as cities expanded, populations shifted, and repairs introduced small improvements over time. Rather than remaining frozen exactly as it had first been built, many systems evolved gradually, while preserving the same fundamental engineering principles established by their original designers. Archaeologists studying these later repairs often uncover fascinating details about the people who maintained the aqueducts across successive generations. Different styles of masonry reveal where damaged sections were rebuilt centuries after the original construction. Replacement stones sometimes bear the marks of later craftsmen, while repaired channels show subtle improvements based upon experience gained through years of operation. These discoveries remind us that the aqueducts were never simply monuments completed on a single day. They were working systems cared for by countless individuals whose names history rarely recorded, but whose efforts allowed fresh water to continue flowing long after the original builders had passed away. This continuous care explains why Roman aqueducts still command such admiration today. They were not remarkable because they achieved the impossible through complicated machinery. Every surveyor measuring a distant hillside, every mason shaping another block of stone, every maintenance worker cleaning sediment from a hidden tunnel, and every engineer checking the gentle slope of the channel contributed to a system whose quiet success would outlast the empire that built it. Even after nearly 2,000 years, the steady flow of those ancient waterways continues reminding us that some of the world's greatest engineering achievements are also among its simplest. By the time the Roman Empire reached its greatest extent, aqueducts had become as essential to a city as its defensive walls, roads, or marketplaces. A prosperous city was expected to provide dependable water, and the presence of an aqueduct often became a visible sign that the community enjoyed Roman engineering, Roman organization, and Roman investment. Travelers approaching from the countryside frequently spotted the graceful arches crossing distant valleys before they ever reached the city itself. Behind every bridge stood an invisible network of tunnels, channels, reservoirs, and maintained infrastructure working together to sustain daily life. The aqueducts also demonstrated something that modern engineers still recognize today. The most successful infrastructure often disappears into the background because it functions so reliably that people rarely think about it. Citizens simply expected clean water to flow from public fountains each morning. Bathhouses opened their doors without questioning whether enough water would arrive. Gardens remained green, workshops continued operating, and households filled their clay jars without considering the remarkable journey the water had completed before reaching them. Only when repairs temporarily interrupted the flow did most people fully appreciate how much their daily lives depended upon the quiet success of the aqueduct beyond the city walls. This reliability required remarkable discipline from the officials responsible for operating the system. Roman administrators carefully monitored the condition of channels, bridges, settling tanks, and distribution basins throughout the year. Crews received instructions to inspect vulnerable sections after storms, clear vegetation growing too close to important structures, and repair small cracks before they expanded into larger problems. Records from the Roman world suggest that protecting the water supply became a matter of considerable public importance because interruptions affected everything from household routines to public baths and commercial activity. Maintaining the aqueduct, therefore, became an ongoing responsibility rather than a project that ended once construction had been completed. Water theft presented another challenge that Roman officials occasionally confronted. Because aqueducts carried such valuable resources, some landowners attempted to divert small amounts of water for private fields, gardens, or workshops by creating unauthorized openings in the channels. Even seemingly minor diversions could reduce the amount reaching neighborhoods farther downstream. Roman law eventually established strict regulations governing who could connect to the water supply and how much water each authorized connection could receive. Inspectors periodically examined the system to identify illegal diversions and ensure that public fountains and other essential services continued receiving the water intended for them. These regulations reveal that managing a great engineering system required thoughtful administration just as much as careful construction. The Romans also understood that different types of water served different purposes. Springs producing exceptionally pure water were often reserved primarily for drinking, while supplies containing higher concentrations of naturally dissolved minerals could be directed toward baths, fountains, irrigation, or industrial uses where taste mattered less. Some cities even received water from several different aqueducts simultaneously, allowing engineers to balance supplies according to seasonal conditions and changing demand. This careful management reflected an increasingly sophisticated understanding that the quality of a water source could be just as important as the quantity it provided. Children grew up hearing the gentle sound of fountains in public squares. Merchants arranged meetings beside flowing water. Visitors admired impressive bathhouses supplied by distant mountain springs. Artists incorporated fountains and aqueducts into mosaics and sculptures celebrating the prosperity of Roman life. Today, it becomes remarkable how little energy the entire system required. Modern cities often depend upon enormous pumping stations, electric motors, treatment facilities, and computerized control systems to move water from distant reservoirs into homes and businesses. Roman aqueducts accomplished much of the same fundamental task without consuming fuel or electricity. Once the route had been carefully surveyed and the channels properly constructed, gravity worked continuously, 24 hours a day, every day of the year. The earth itself provided the energy. Roman engineers simply learned how to guide that natural force with precision, creating infrastructure so elegant in its simplicity that it continues inspiring engineers nearly 2,000 years after the first mountain springs began their quiet journey toward the cities of ancient Rome. As interest in Roman engineering grew during the Renaissance and later centuries, architects, surveyors, and scholars began traveling across Europe to study the surviving aqueducts in remarkable detail. They measured the height of arches, examined the precision of the stonework, traced forgotten routes through the countryside, and carefully recorded the dimensions of channels that had continued carrying water long after the empire itself had disappeared. Many arrived expecting to find simple ancient structures. Instead, they discovered engineering so sophisticated that it challenged many of their assumptions about what people living nearly 2,000 years earlier had been capable of accomplishing. By the 19th century, when modern civil engineering began emerging as a formal profession, Roman aqueducts had become valuable case studies for students learning how to design large infrastructure projects. Engineers admired the careful surveying, the efficient use of local materials, the elegant distribution of weight through stone arches, and the extraordinary longevity of the structures themselves. They recognized that while construction technology had advanced considerably, many of the fundamental engineering principles remained unchanged. Water still followed gravity. Stable foundations remained essential. Careful planning still prevented costly mistakes. Durable materials still determined how long a structure would survive. In many respects, the Roman aqueduct served as one of history's earliest engineering textbooks, written not with words, but with stone. Modern technology has allowed researchers to investigate these ancient systems in ways their builders could never have imagined. Ground-penetrating radar detects buried channels without disturbing the soil above them. Laser scanners record millions of individual measurements every second, producing incredibly accurate three-dimensional models of bridges, tunnels, and distribution tanks. Computers combine these measurements with satellite data to recreate entire aqueduct systems digitally, allowing engineers to study how water flowed through them under different conditions. Scientists have also begun examining the mineral deposits left behind inside ancient channels. As hard water flowed through the aqueducts over hundreds of years, thin layers of calcium carbonate slowly accumulated along the walls. These deposits act almost like the growth rings of a tree, preserving chemical information about the water itself. By carefully analyzing these layers, researchers can estimate how long particular aqueducts remained in operation, identify periods when repairs interrupted the flow, and even learn about ancient climate conditions by studying changes in the mineral composition over time. The water that once quietly sustained Roman cities continues providing valuable information nearly 2,000 years later. Environmental scientists have found additional reasons to admire the Roman approach. Once completed, an aqueduct required remarkably little outside energy to operate. Gravity performed the work continuously without producing smoke, consuming fuel, or generating noise. The system relied upon renewable natural processes, as rain replenished mountain springs and elevation provided the force needed to move the water. Although modern cities face challenges far beyond those of ancient Rome, many engineers now recognize that gravity-fed systems remain among the most energy-efficient methods of transporting water whenever geography allows. In an age increasingly focused on sustainability, the quiet wisdom of Roman engineering has gained renewed relevance. This is one of the most enduring lessons offered by the aqueducts. Great engineering does not always depend upon adding more complexity. Roman engineers did not invent gravity, groundwater, or the natural flow of water downhill. That philosophy allowed a single mountain spring to support thriving cities for centuries, proving that careful observation can often achieve results that brute force never could. Standing beside a surviving Roman aqueduct today, it is easy to admire the graceful arches stretching across the landscape or the weathered stone that has endured through countless generations. Yet the true achievement lies not only in what can still be seen, but also in what those structures quietly represent. Every surviving aqueduct remains a silent conversation between the ancient world and our own, carried forward by the same gentle flow of water that first began its remarkable journey high in the mountains nearly 2,000 years ago. The greatest compliment that can be paid to the Roman aqueduct is that it still influences the way engineers approach problems today. Modern cities may rely upon powerful pumps, advanced treatment plants, computerized monitoring systems, and pipelines stretching for hundreds of miles. Yet the planning process often begins with many of the same questions Roman surveyors asked nearly 2,000 years ago. Where is the cleanest source of water? What is the most efficient route across the landscape? How can gravity reduce the amount of energy required? Which building materials will last the longest with the least maintenance? The technology has changed dramatically, but the engineering philosophy remains familiar. Civil engineers frequently describe infrastructure as something people notice only when it stops working. Roads attract attention when traffic comes to a halt. Bridges become important when they close for repairs. Electrical systems are appreciated most during power outages. Water systems follow the same pattern. The Roman aqueduct achieved that same quiet success. Its greatest accomplishment was not simply transporting water across the countryside, but making the extraordinary seem completely ordinary through years of dependable service. The aqueducts also demonstrate that some of humanity's greatest achievements are built upon invisible foundations. Visitors standing beneath the Pont du Gard or the aqueduct of Segovia naturally admire the graceful arches rising high above the landscape. Yet they rarely see the careful surveying that determined the route years before construction began. They cannot observe the calculations that established the perfect gradient, the the quarry workers shaping thousands of individual stones, or the maintenance crews who patiently clean the channels generation after generation. Every visible structure rests upon countless unseen contributions made by people whose names history has largely forgotten. Their quiet dedication became just as important as the magnificent bridges that continue inspiring visitors today. Another remarkable aspect of the aqueducts is how effectively they balance strength with efficiency. Roman engineers never built larger structures than necessary simply to impress observers. Every bridge, tunnel, retaining wall, and channel reflected careful consideration of the landscape and the amount of water that needed to be transported. Stone was expensive to quarry and difficult to move, so every block served a purpose. Labor required years of coordinated effort, so every decision had to justify the enormous investment of time and resources. This thoughtful approach produced structures that appear both elegant and practical, demonstrating that efficiency and beauty often emerge together when engineering is guided by careful planning rather than unnecessary excess. As archaeologists continue uncovering forgotten sections of ancient aqueducts, they often discover evidence that later generations repaired, modified, and expanded the original systems instead of abandoning them. New channels connected growing neighborhoods, damaged bridges received additional reinforcement, and distribution tanks were enlarged as populations increased. These changes revealed that Roman engineering was never static. The aqueducts evolved alongside the communities they served, adapting to changing needs while preserving the careful principles established by their original designers. They resembled living systems that matured over time rather than monuments frozen in the moment they were first completed. Looking across the nearly 2,000 years since the first Roman aqueducts began carrying mountain water toward distant cities, one lesson quietly emerges again and again. Great engineering is rarely about defeating nature. The Romans did not force water to behave differently. They simply observed that it always sought the lowest point, and then designed a path that allowed gravity to guide every drop exactly where it was needed. That elegant partnership between human ingenuity and the natural world transformed a simple mountain spring into the lifeblood of one of history's greatest civilizations, leaving behind a legacy that continues flowing through the practice of engineering even today. Beyond the remarkable engineering, Roman aqueducts also changed the relationship between people and water in ways that are easy to overlook today. Before these systems existed, water often dictated where a community could survive. Settlements clustered beside rivers, lakes, and natural springs because daily life depended upon being close to a dependable source. The aqueduct reversed that relationship. Instead of people moving to the water now traveled to the people. Cities gained the freedom to expand across hillsides, valleys, and plateaus that would previously have been impractical, knowing that a carefully engineered channel could quietly deliver fresh mountain water wherever it was needed. This new freedom influenced the appearance of Roman cities as much as it influenced their daily routines. Architects designed larger public squares because nearby fountains could supply the growing crowds. Bathhouses expanded into enormous complexes, filled with warm pools, cold pools, steam rooms, and gardens. Decorative fountains became common, not only because they were beautiful, but because a constant overflow of fresh water demonstrated the reliability of the city's infrastructure. Visitors arriving from regions without aqueducts must have found these sights astonishing. To them, water appeared almost effortless, flowing continuously through streets and public spaces where only a generation earlier every bucket would have needed to be carried by hand. The psychological effect of that dependable supply should not be underestimated. Knowing that clean water would be available tomorrow, next month, and next year encouraged confidence in the future. Builders invested in larger homes. Merchants established permanent businesses. Public officials planned ambitious construction projects, knowing the city's water supply could support continued growth. Reliable infrastructure often creates opportunities that extend far beyond its original purpose, and the Roman aqueduct became a perfect example of that principle. Even the sounds of a Roman city reflected the presence of the aqueduct. Instead of silence broken only by footsteps and conversation, many public spaces echoed with the gentle music of flowing water. Fountains spilled steadily into stone basins before overflowing into carefully designed drainage channels. Bathhouses hummed with the quiet movement of fresh water entering pools throughout the day. Gardens remained filled with birds attracted to dependable water sources, while travelers refreshed themselves beside public fountains before continuing their journeys. The aqueduct shaped not only the appearance of the city, but also its atmosphere, creating an environment where the sound of flowing water became part of everyday life. As centuries passed, those familiar sounds continued through periods of peace and uncertainty alike. Emperors came and went. Governments changed. Roads were repaired. Buildings expanded. And generations grew old. Yet the water continued following the same measured route, first established by Roman surveyors many years earlier. Every sunrise brought another fresh supply, descending quietly from the mountains, crossing valleys, winding through tunnels, entering settling tanks, filling fountains, supplying bathhouses, and eventually leaving the city to continue its natural journey downstream. The aqueduct became a steady companion to daily life, so dependable that most citizens rarely pause to consider the extraordinary engineering making it all possible. That quiet reliability explains why the Roman aqueduct remains one of history's greatest engineering achievements. It was designed to perform the same essential task every hour of every day, year after year, century after century, asking for little attention while improving the lives of everyone it served. Few inventions have accomplished so much while demanding so little recognition. In its calm, uninterrupted flow, the Roman aqueduct demonstrated that the finest engineering often succeeds not by drawing attention to itself, but by becoming such a dependable part of everyday life that people can no longer imagine living without it. Today, millions of people visit the surviving Roman aqueducts without realizing that they are walking beside ideas that continue shaping the modern world. Children stand beneath the soaring arches of the Pont du Gard in France. Travelers photograph the towering granite stones of the Aqueduct of Segovia in Spain, and hikers discover forgotten channels winding quietly through the Italian countryside. At first glance, these monuments appear to belong entirely to history, silent reminders of an empire that vanished long ago. Yet the principles hidden within their stone remain very much alive. Every modern reservoir supplying a city by gravity, every carefully surveyed pipeline descending from a mountain watershed, and every engineer calculating the most efficient route across a landscape owes something to the quiet lessons first demonstrated by these remarkable Roman waterways. One reason the aqueducts continue inspiring admiration is their extraordinary honesty. Every part of the structure serves a clear purpose. The arches support the channel above. The channel carries the water. The settling tanks remove sediment. The inspection shafts allow maintenance. Nothing exists purely for decoration, yet the finished result possesses a timeless elegance that architects still admire today. This harmony between beauty and function appears again and again throughout Roman engineering. Instead of adding ornament after the work was complete, the Romans allowed good engineering itself to create beauty. The graceful rhythm of repeating arches, the careful proportions of each bridge, and the quiet confidence of the stonework all emerged naturally from solving practical problems with exceptional skill. Modern structural engineers often point to Roman arches as perfect examples of efficient design. Unlike flat beams that bend under heavy loads, an arch redirects weight outward and downward into its supporting columns. Every stone presses gently against the next, allowing compression rather than tension to carry enormous loads. Stone performs exceptionally well under compression, making the arch one of the strongest structural forms ever developed. This simple geometric principle allowed Roman builders to span rivers and valleys using materials available nearly everywhere in the empire. Even after 2,000 years of weather, earthquakes, and changing landscapes, many of these arches continue standing because their strength comes not from hidden reinforcements, but from the elegant way they distribute force through every carefully shaped block. The aqueducts also remind us that the greatest technological achievements are often surprisingly quiet. Unlike towering monuments built to celebrate military victories or enormous temples constructed to inspire awe, the aqueduct existed primarily to improve ordinary daily life. Its greatest success was measured each morning when clean water reached a public fountain, each afternoon when bathhouses remained supplied, and each evening when households filled their jars without worrying whether enough water would still be available tomorrow. The aqueduct earned its reputation not through dramatic moments, but through centuries of dependable service, proving that consistency can become just as remarkable as spectacle. That is why modern engineers continue speaking about Roman aqueducts with such respect. They recognize that these systems solved an enormously difficult problem using solutions that remain elegant even by today's standards. The Romans did not possess powerful machines capable of correcting careless mistakes during construction. Every survey, every measurement, every tunnel, every bridge, and every stone had to be right from the very beginning. The success of the entire project depended upon careful planning long before construction crews ever lifted the first block into place. It remains a powerful reminder that the quality of an engineering project is often determined long before the visible work begins. Across our journey so far, it is remarkable how a single drop of mountain spring water has quietly guided us through nearly every aspect of Roman civilization. That small drop has introduced us to geology, hydrology, surveying, mathematics, architecture, construction, chemistry, public health, city planning, and the daily lives of millions of people who depended upon its steady arrival. Few engineering achievements connect so many different fields of knowledge so naturally. The journey of that single drop of water does not end when it reaches the city. After filling fountains, supplying bathhouses, serving homes, and supporting workshops, the water continued moving through an equally impressive network of drains and sewers before eventually returning to nearby rivers. The Romans had created a complete water cycle within the city itself. Fresh water entered continuously from the mountains, performed countless useful tasks throughout the day, and then flowed safely away, making room for the next supply already approaching through the aqueduct. This constant movement helped keep the system cleaner than one relying upon stagnant pools or stored reservoirs, demonstrating that Roman engineers understood the importance of circulation, even if they described it in practical rather than scientific terms. The more historians study these remarkable systems, the more they recognize that the aqueduct was never an isolated project. It formed one part of a much larger network connecting roads, bridges, sewers, bathhouses, fountains, reservoirs, and public buildings into a carefully organized whole. Every improvement supported another. Roads allowed stone to reach construction sites. Bridges carried both travelers and water. Quarries supplied the masonry for arches and channels. Sewers completed the journey after the water had served its purpose. The success of the aqueduct depended upon the strength of the entire Roman infrastructure, revealing just how carefully the empire planned its growing cities. This interconnected approach remains one of the defining characteristics of successful engineering today. Modern cities rely upon transportation systems, electrical grids, communication networks, water supplies, wastewater treatment facilities, and countless other services working together continuously behind the scenes. A problem in one system often affects many others. The Romans recognized this relationship remarkably early. They understood that dependable water encouraged healthier cities, stronger economies, more productive workshops, and greater public confidence. The aqueduct therefore became much more than a channel carrying water. It became part of the foundation upon which an entire civilization could continue growing. The sheer scale of these achievements becomes even more impressive when viewed across the entire Roman world. Historians estimate that the empire eventually constructed hundreds of aqueducts, supplying cities spread across 3 continents. Although each system served its own region, they all reflected the same engineering philosophy, built upon careful surveying, thoughtful planning, durable construction, and respect for the quiet force of gravity. Few civilizations have ever created public works on such an ambitious scale, while maintaining such consistent standards of quality. Archaeological discoveries continue adding new chapters to this remarkable story. Excavations regularly uncover forgotten inspection shafts, buried channels, abandoned reservoirs, and sections of tunnel that have remained hidden beneath the earth for centuries. In some locations, mineral deposits preserved inside the channels reveal exactly how high the water once flowed, while repair marks carved into the masonry record the work of maintenance crews who kept the system operating long after the original builders had finished their task. The most remarkable aspect of the Roman aqueduct is that its greatest innovation was not a machine, a new material, or a complicated invention. It was a way of thinking. Roman engineers began every project by carefully observing the natural world instead of attempting to overpower it. They accepted that gravity would always pull water downhill, that mountains and valleys could guide the route rather than prevent it, and that patient planning would accomplish far more than hurried construction. Their greatest resource was not advanced technology. The Roman aqueduct also teaches us an important lesson about the value of simplicity. Throughout history, some of humanity's greatest inventions have depended upon increasingly complex machines, but the aqueduct achieved its success by removing complexity wherever possible. Once the channel had been carefully surveyed and constructed, there were no engines to fuel, no gears to lubricate, and no machinery that needed constant adjustment. Gravity never required maintenance. It never grew tired, consumed resources, or stopped working because of changing seasons. This remarkable reliability gave the Roman Empire an enormous advantage. Cities no longer needed to organize endless lines of people carrying buckets from distant wells. Public officials could plan for future growth with confidence because they knew additional neighborhoods would have access to dependable water. Merchants, established businesses, knowing fountains and bathhouses would continue attracting customers. Builders designed larger public spaces because they no longer worried about where fresh water would come from. Even visitors arriving from distant provinces immediately recognized the prosperity that a reliable water supply made possible. The aqueduct quietly influenced commerce, health, architecture, agriculture, and daily life without demanding attention for itself. As centuries passed, many civilizations admired these remarkable structures, but struggled to match them. Building an aqueduct required far more than the ability to stack stones into graceful arches. It demanded generations of accumulated knowledge about surveying, geology, construction, mathematics, hydraulics, and long-term maintenance. Losing any one of those skills made reproducing the complete system far more difficult. This helps explain why some medieval communities continued using Roman aqueducts long after they had forgotten exactly how the original engineers designed them. The structures themselves survived, but much of the practical knowledge that created them had gradually faded with time. Modern engineering has gradually rediscovered many of those same principles through science rather than apprenticeship. Today we understand groundwater, fluid dynamics, structural mechanics, and material science in extraordinary detail. Yet despite all these advances, engineers continue arriving at many of the same conclusions reached by Roman surveyors nearly 2,000 years ago. Careful planning prevents expensive mistakes. Durable materials reduce long-term maintenance. Working with the landscape usually proves more efficient than fighting against it. Gravity remains one of the most dependable sources of energy available whenever geography makes it possible. This is why Roman aqueducts continue appearing in engineering textbooks, university lectures, and archaeological research around the world. They are not studied simply because they are ancient. Every surviving channel, bridge, tunnel, and settling basin reminds us that successful engineering begins by understanding the problem completely before searching for a solution. The Romans resisted the temptation to overcomplicate their designs. High in the mountains, rain falls upon rocky slopes before slowly filtering into the ground. Months later, cool spring water emerges from hidden underground reservoirs. Gravity begins its patient work, carrying each drop downhill through forests, valleys, and open countryside. Nearly 2,000 years ago, Roman engineers recognized that they did not need to change this timeless process. They simply needed to guide it. Although the Roman Empire eventually came to an end, many of its aqueducts refused to disappear with it. Long after emperors, governors, and legions had passed into history, fresh water continued following the same carefully surveyed channels first laid out centuries earlier. In some regions, local communities repaired damaged sections whenever they could because they recognized the immense value of a dependable water supply. Even where parts of an aqueduct eventually fell into disrepair, surviving stretches often remained useful for generations, quietly serving towns whose inhabitants no longer remembered the names of the original engineers who designed them. The structures themselves had become part of the landscape, enduring through changing kingdoms, languages, and cultures while continuing to perform the simple task they had always been built to accomplish. Time, however, gradually transformed these working waterways into historical treasures. Trees grew beside forgotten channels. Wildflowers appeared between weathered stones. Soil slowly covered long buried tunnels, while only the tallest bridges remained visible above the surrounding countryside. Travelers passing beneath their graceful arches often paused to admire their enormous size, wondering how ancient builders had managed such extraordinary construction without modern equipment. Artists sketched the surviving monuments, historians recorded their observations, and early archaeologists began tracing the forgotten routes that once carried fresh mountain water across the Roman world. With every passing century, the aqueducts slowly changed from essential infrastructure into one of humanity's most admired engineering achievements. Engineers carefully inspect ancient masonry for signs of movement, while archaeologists document newly discovered sections before they can be damaged by development or natural erosion. Vegetation growing between stones is removed where necessary. Damaged joints are repaired using materials chosen to match the original construction, and detailed digital models preserve every visible feature with extraordinary accuracy. This work requires the same qualities that first created the aqueducts nearly 2,000 years ago: patience, careful observation, and respect for the remarkable craftsmanship of those who came before. The aqueducts have also become places of education and inspiration. Students of engineering visit them to study structural design. Architects admire the graceful proportions of the arches. Historians explore the societies that depended upon their flowing water, while archaeologists continue uncovering new evidence hidden beneath the landscape. Few ancient monuments connect so many different fields of knowledge, while remaining so immediately understandable to anyone who stands beside them. That is the greatest reason Roman aqueducts continue capturing our imagination after nearly 2,000 years. They remind us that remarkable engineering is not always about creating something loud, complicated, or dramatic. The Romans never expected their aqueducts to become famous monuments admired by millions of visitors centuries later. They simply wanted clean water to reach their cities every single day with dependable precision. In accomplishing that goal so completely, they created one of history's greatest examples of thoughtful engineering, proving that the simplest ideas, when guided by patience, observation, and extraordinary craftsmanship, can leave a legacy that continues flowing through history long after the final stone has been laid. One of the quiet themes running through the entire story of the Roman aqueduct is trust. Every morning, millions of people awoke, expecting fresh water to be waiting for them. They trusted that somewhere beyond the distant hills, mountain springs continued flowing. They trusted that hidden channels beneath fields and forests remained clear. They trusted that bridges spanning broad valleys still stood strong, that maintenance crews had done their work well, and that gravity would continue guiding each drop toward the city exactly as it had the day before. Most citizens never met the engineers who designed the aqueduct or the workers who maintained it, yet their daily lives depended upon those unseen efforts. The aqueduct became one of the earliest examples of public infrastructure quietly earning the confidence of an entire civilization. That trust extended far beyond the city itself. Farmers cultivating land near the aqueduct understood that the nearby towns would continue thriving because dependable water supported growing populations. Merchants traveling Roman roads could rely upon public fountains in unfamiliar cities. Soldiers stationed hundreds of miles from Rome found many of the same carefully designed water systems serving distant provinces. The aqueduct became one of the invisible threads helping connect an enormous empire, giving communities separated by mountains and seas access to the same remarkable engineering traditions. Although languages, customs, and local landscapes differed greatly from one province to another, the gentle sound of fresh water flowing into a stone fountain became a familiar reminder of Roman organization and planning. The Romans certainly admired impressive architecture, yet they devoted equally great effort to structures that remained almost entirely hidden beneath the ground. This willingness to dedicate years of planning, construction, and maintenance toward improving ordinary daily life speaks volumes about the importance they placed upon practical engineering. The aqueduct was not built simply to impress visitors. Modern historians often describe Roman aqueducts as masterpieces of civil engineering, and the description is remarkably appropriate. The word civil comes from the idea of serving citizens, and few engineering achievements have done so more effectively. Every measured slope, every tunnel carved through solid rock, every bridge spanning a valley, and every settling tank quietly removing sediment existed for one purpose: improving the lives of the people who depended upon them. Long after military victories faded into history and political boundaries changed, the aqueducts continued fulfilling that purpose with quiet reliability. Their greatest triumph was not that they survived for centuries, but that they made those centuries better for the communities they served. As archaeologists, engineers, and historians continue studying these silent waterways, they are reminded that some of history's greatest achievements do not announce themselves with noise or spectacle. Instead, they reveal their greatness through consistency. Day after day, season after season, year after year, the Roman aqueduct quietly accomplished exactly what it had been designed to do. Fresh mountain water entered the channel, followed the gentle path chosen by careful surveyors, crossed valleys on graceful arches, passed beneath fields through hidden tunnels, flowed into fountains and bathhouses, and finally continued on its natural journey beyond the city. Even after spending nearly 2,000 years exposed to changing weather, earthquakes, wars, and the slow passage of time, many Roman aqueducts continue standing with remarkable dignity. Their survival is not the result of chance. It reflects thousands of careful decisions made long before construction ever began. Surveyors selected stable ground whenever possible. Engineers calculated gentle gradients that reduced unnecessary stress on the channels. Builders chose durable stone, capable of withstanding centuries of use, while maintenance crews faithfully inspected the system year after year, correcting small problems before they could become larger ones. Every stage contributed to a structure designed not merely to function for a single generation, but to endure for many that would follow. This remarkable longevity has given modern scientists an opportunity that few ancient engineering projects can offer. Instead of studying only written descriptions or scattered ruins, researchers can still walk through original tunnels, climb surviving inspection shafts, examine the waterproof mortar lining the channels, and measure the graceful arches exactly as Roman builders left them centuries ago. Every surviving section becomes an open textbook, allowing engineers to compare ancient solutions with modern practices. The aqueducts continue teaching because they remain standing, preserving within their stone not only the finished structures, but also the thinking that created them. No lesson appears more clearly than the importance of planning before construction begins. Roman engineers understood that mistakes become increasingly expensive once thousands of workers have already begun building. For that reason, they devoted extraordinary effort to surveying the landscape, confirming measurements, evaluating materials, and selecting the most practical route before laying the first stone. Modern engineering follows the same philosophy. Months or even years may be spent studying the ground, analyzing environmental conditions, preparing detailed drawings, and testing materials before construction equipment ever arrives at a site. The tools have changed beyond recognition, yet the principle remains almost identical to that practiced by Roman surveyors standing quietly on distant hillsides nearly 2,000 years ago. The aqueducts also remind us that successful engineering rarely depends upon overpowering nature. Instead, it begins by understanding the natural world deeply enough to allow its own forces to perform the work. Gravity carried every drop of water, mountains provided dependable springs, stone supplied strength, volcanic ash produced durable concrete. Rather than attempting to replace these natural processes, Roman engineers carefully observed them, learned from them, and designed systems that worked alongside them. Their greatest achievement was not creating a new force of nature. It was recognizing how to guide the forces that had always existed. Across our journey, from the first mountain spring quietly emerging among the rocks, to the bustling streets of ancient Rome, filled with flowing fountains and crowded bathhouses, it becomes remarkable how much depended upon one simple idea. Water naturally flows downhill. Everything else, the careful surveying, the hidden tunnels, the towering bridges, the settling tanks, the distribution basins, and the thriving cities themselves, grew from understanding that one fundamental truth. Sometimes the greatest engineering accomplishments begin not with discovering something entirely new, but with seeing something familiar more clearly than anyone had before. The Roman aqueduct stands as timeless proof that patience, observation, and respect for the natural world can transform one of nature's simplest movements into one of history's greatest achievements. There is another reason Roman aqueducts continue earning such admiration from historians and engineers alike. They demonstrate that true innovation is often invisible once it succeeds. Visitors standing beneath a surviving aqueduct naturally notice the towering arches stretching across the landscape, yet they rarely think about the countless calculations hidden within those graceful lines. Every arch rests exactly where surveyors intended. Every stone carries only the amount of weight it was designed to support. Every section of channel maintains the gentle slope needed to keep the water moving. Nothing appears forced or overly complicated because the engineering has become almost effortless. That quiet elegance is often considered the highest compliment any engineer can receive. When a system works perfectly, it begins to feel as though it could never have been built any other way. The aqueducts also reveal something important about the relationship between engineering and time. Many modern construction projects are judged by how quickly they can be completed, but Roman engineers measured success differently. Every decision reflected that long perspective. A stronger foundation justified the additional effort. Better stone was worth the longer journey from the quarry. More accurate surveying deserved extra weeks of careful measurement if it prevented future repairs. Instead of asking how quickly something could be built, Roman engineers often asked how long it could continue serving the people who depended upon it. That way of thinking helped create structures that still stand nearly 2,000 years later. This long view also shaped the way maintenance was approached. The Romans never imagined that an aqueduct would remain perfect forever. Rain would fall, earthquakes would occur, mineral deposits would slowly accumulate inside the channels. Stones might loosen after centuries of changing seasons. Rather than viewing these changes as failures, they accepted them as natural parts of the system's life. Regular inspections, careful repairs, and patient maintenance became just as important as the original construction itself. In many respects, the aqueduct was never truly finished. Modern infrastructure follows much the same pattern. Bridges are inspected regularly, reservoirs are monitored continuously, pipelines receive routine maintenance, and water treatment facilities operate every hour of every day. Behind every dependable system stands a dedicated group of engineers, technicians, and maintenance crews whose work often goes unnoticed because problems are prevented before they ever become visible. The Roman aqueduct reminds us that this quiet dedication has always been one of the foundations of successful engineering. Extraordinary structures are rarely sustained by extraordinary moments alone. They endure through thousands of ordinary days of careful attention. That is why the Roman aqueduct remains one of history's greatest engineering achievements. It was never designed to inspire admiration through complexity or spectacle. Every drop of mountain water followed the same patient journey, descending gently through tunnels, across bridges, into fountains, and finally through the city before continuing onward once again. Even today, as fresh water continues flowing through modern cities around the world, the quiet lessons first demonstrated by the Roman aqueduct remain as relevant as they were nearly 2,000 years ago. As our journey through the remarkable world of Roman aqueducts slowly comes to an end, these extraordinary structures were never simply channels carrying water from one place to another. From the moment rain fell upon distant mountains, every stage of the journey depended upon forces that had existed for millions of years. Water filtered quietly through layers of rock before emerging from cool springs. Gravity gently guided each drop downhill. Skilled surveyors discovered the perfect path across valleys and hillsides, while thousands of craftsmen transformed stone, lime, volcanic ash, and timber into a system capable of serving an empire. Together, they created an engineering achievement whose quiet reliability would outlast the civilization that built it. The Roman builders never tried to overpower nature. Instead, they studied it with patience, respected its rules, and allowed those rules to become the foundation of every decision they made. Gravity became their engine. Mountains became their reservoirs. Stone became their framework. Water itself became their constant partner. By working with the landscape rather than against it, they solved one of the greatest challenges facing the ancient world and transformed the daily lives of millions of people. Nearly 2,000 years later, engineers continue following many of those same principles whenever they design dependable infrastructure intended to serve communities for generations. Today, the surviving aqueducts continue standing quietly across Europe, North Africa, and the Middle East, their graceful arches stretching across valleys while their hidden channels remain buried beneath fields and hillsides. Some still carry fresh water, while others now serve as open classrooms where archaeologists, historians, architects, and engineers continue discovering new lessons preserved within their weathered stone. Every surviving bridge, tunnel, settling basin, and distribution tank reminds us that true innovation often leaves its greatest mark not through spectacle, but through steady service carried out day after day, year after year, century after century. The Roman aqueduct remains one of history's finest examples of thoughtful engineering because it solved an essential problem with such elegance that its greatest success became almost invisible to the people who depended upon it. Across our entire journey, from a single mountain spring high above the countryside to the bustling streets, fountains, bathhouses, and gardens of ancient Rome, we have followed one quiet stream of water through geology, hydrology, surveying, mathematics, architecture, construction, chemistry, archaeology, and the everyday lives of one of history's greatest civilizations. Few engineering achievements connect so many different fields of knowledge while remaining so beautifully simple at their core. The Roman aqueduct reminds us that the greatest ideas often begin with careful observation, grow through patience and shared knowledge, and endure because they continue improving the lives of others long after their creators have disappeared into history. It is a timeless reminder that when human curiosity works in harmony with the natural world, even a single drop of water can help shape the course of civilization. Thank you for joining me on tonight's journey through the silent engineering of ancient Roman aqueduct systems. If you enjoyed this peaceful exploration through history, science, engineering, and archaeology, I'd love for you to subscribe and join us again. New sleep stories are posted every other day, and you'll find many more relaxing journeys waiting for you in our growing collection of playlists. Until next time, sleep well, dream peacefully, and I'll see you in the next story.